Hi, my name is Hashim, and the work I'm presenting today is titled Developing an OpenMP Runtime for UVM-capable GPUs. This work is in conjunction with my advisor at UIUC, Vikram Adve, and our collaborators, Finkel at Argonne Lab and Lingda at Brookhaven. So I'll start with a bit of introduction of heterogeneous programming and why it's interesting. Well, heterogeneous programming is a paradigm where you have these different types of processors working in conjunction with each other. And it's interesting because you can specialize different application tasks according to their particular computation needs. For instance, you can have GPUs and many core CPUs work in conjunction, and they can be specialized for different tasks. For instance, for serial processing, you can have many core CPUs. For massively parallel applications, which are more throughput bound, you can have GPUs. And interestingly, OpenMP now includes support for heterogeneous programming. You can actually target your OpenMP regions for different target devices. In this particular talk, I'm mostly going to be talking about GPUs, and in particular, CUDA Unified Virtual Memory. What is CUDA Unified Virtual Memory? Well, CUDA Unified Virtual Memory is this abstraction that gives you a single address space across all the GPUs and the CPUs in the system. And this was introduced as part of the Kepler architecture in 2014. And now it's gone a step further, and as part of the Pascal architecture, it includes an automatic page migration engine which allows you to fetch pages on demand. And moreover, this allows, and because of this particular technology, now you can fetch pages on demand. You do not have the existing limitation that was with Kepler architecture, where you had to copy all the data before the kernel had to be launched. Moreover, in the Pascal UVM architecture, you're no longer limited by device memory. You're only limited by the overall system memory size, which is useful because you can run on very large data sets now. So this is an example which shows you how traditional CUDA compares to CUDA UVM. You know, it's a vectorized example. You just take two vectors, x and y, adds the result back and returns the result in vector z. And essentially what you see right over here is that they're explicit data copies. You're explicitly copying host buffers onto device buffers and then launching the kernel that does the vector addition. On the right, where you have the CUDA UVM code, you see that there are no explicit copies. You're just allocating memory in the unified virtual memory space, and you just launch the kernel, and the memory can be fetched on demand, essentially. Now, how does talk about OpenMP supporting heterogeneous systems and heterogeneous programming? How does this really look in the picture? So, OpenMP was traditionally supposed to be used as a shared memory parallelism, where you have these multiple threads running on different processors, sharing the same physical memory, and they have shared data, and they access the shared data from the same memory space. Now, with accelerators coming to the picture that are mostly attached with an external bus, such as PCI Express, now OpenMP must include these new directives that allow you to map data, explicitly map data for target accelerators, essentially. How does this look in code? Well, here you have an OpenMP sort of OpenMP program. You have Saxpy. Essentially, the input vectors are x and y. You're calculating an expression and you're storing the result back in y. And two important things here. Firstly, with the OpenMP loop, you have a target construct. The target clause here specifies that this loop should be compiled for an accelerator. The accelerator to which it is compiled for is specified in the command line when you're compiling the program. And then, very importantly, you have these data mapping clauses that specify which data needs to be copied to the device before the execution can begin. And you can see that explicitly there's a direction of copy as well. For the x vector, because it's just an input vector, doesn't need to be copied back, the direction is 2. With y, because it's also the output, the direction is 2 from. You copy it and you also have to copy it back. So how does OpenMP offloading really work in practice? So there's this effort known as Libomptarget. This is an OpenMP offloading runtime. Is an effort by multiple vendors, including Intel and IBM, and essentially it enables offloading. And this is how the binary looks like when you're compiling an OpenMP program with target support. In addition to the host code right here, you also have the device code. And the device code is compiled for the OpenMP constructs, for which you had the target class, essentially. And in the general case, you had the host code interacting with the host OpenMP runtime. The host OpenMP runtime includes these routines that implement the parallelization for the host part. If you have an OpenMP loop and you're running on the CPU, this runtime implements that parallelization. But in addition to that, now because target constructs are coming into the picture, you have an offloading runtime, LibOmpTarget, which implements the underlying API for offloading. And an important thing to notice here is that this particular runtime is device agnostic. It's not specific to any particular device. In fact, on the back of this, you have device-specific plugins that do device-specific operations. In this case, because we've been talking about CUDA, you have a CUDA device plugin on the back end. And it essentially does device-specific operations, for instance, copying data to the GPU or launching kernel execution. And that plugin in turn calls the CUDA driver API to do the actual device-specific operations. Now coming to what we have been doing with this runtime and with UVM in general, we built this OpenMP framework for UVM, and the goal is essentially to make OpenMP work with UVM architectures in a performant way. Another goal, other than performance, is to have performance portability. We don't want our architecture to be fundamentally confined only to UVM. And to achieve these goals, there are some design considerations. For instance, what information can you use from OpenMP to actually have such good performance? For instance, we just showed you the OpenMP target clauses. Can we use these data mapping clauses to actually improve performance? Moreover, with UVM, as data sets are no longer limited by device memory, you can have really large data sets, and you're only limited by system memory size. Can you make performance scale with large data sets? And this again is one of our goals. So what is this framework really composed of? The framework is composed of two major components. You have a compiler component and you have a runtime component. And the compiler component essentially extracts application-specific information and feeds it to the runtime. And the runtime uses this information to do certain optimizations. I'll show the optimizations in a minute and how these two things essentially interact. For instance, this application-specific information could be data access probabilities. How likely is a certain piece of data to be accessed? Because if it's likely to be accessed, maybe we should copy in advance. We'll talk about this more later. Then comes in the OpenMP runtime. So I showed you the OpenMP runtime implementation LibOmpTarget, which implements the API for offloading. We essentially extend that. In particular, we extend the CUDA device plugin. And we firstly make it UVM compatible. It didn't have support for UVM architectures, we made it UVM compatible. Also, we incorporate a couple of UVM specific optimizations that we show improve performance quite significantly. So, starting with optimizations, the interesting part. And the first optimization that we implement is prefetching. And this essentially, so this is how it boils down. When you have, on the left side, you have an OpenMP code, same code, Saxpy. You have x and y are the input vectors, and then you're computing expression, saving it back to y. Essentially, when this code is compiled, this maps down to an API call into the runtime right here, execute target region, which essentially invokes the computation kernel. And the important thing to note here is that with UVM, you don't really need to have any data copies because data can be fetched on demand, right? But interestingly and importantly, the CUDA driver API does include API that allows you to prefetch that data in advance if you know the data you're accessing. And that basically is important or interesting because it reduces the page fault processing overhead, which actually becomes quite significant. So this particular prefetching optimization, how does this work in practice? So you have the compiler side. The compiler extracts certain information. The goal of the compiler, especially here, is to extract data access probabilities. Because if a data is likely to be accessed, we want to prefetch it. If it's not likely to be accessed, let it demand page. And so here comes the application source. We compile it to LLVM and then profile the application on representative inputs. And then comes into the picture a compiler transformation that extracts these probabilities and associates them with the data variables in the program. Then is another compiler transformation that packs this information, the access probabilities up, and emits a transformed IR. The transform IR now includes this application-specific information, data access probabilities, and it's built into this final executable. Now when you have this executable, the executable is going to interact with the runtime. So I'm going to show you the workflow for the runtime. So you have this executable with packed up with the access probabilities. It makes calls to the offloading runtime to actually offload a particular kernel onto a target accelerator, and now includes the access probabilities. The offloading runtime for doing the device-specific stuff calls the CUDA device plugin. The CUDA device plugin uses a cost model and the cost model uses these access probabilities to actually determine if it's profitable to copy that data as well. And the cost model includes, the application-specific information, which is the access probabilities. Also, it has some hardware-specific constants, which will vary with different interconnects. And then, based on whatever decision this runtime makes, it decides to prefetch, to either prefetch or not prefetch, and then initiates prefetching between the host memory and the device memory. So that was the prefetching optimization. The other problem that comes up with UVM is memory oversubscription. Because now you can have data sets larger than device memory, that doesn't necessarily mean that you have good performance. And the particular reason for this, especially if you look at it in the context of the prefetching optimization, naive prefetching optimization, is that if you prefetch data and then compute it, if the data that you're prefetching is larger than device memory, essentially you're going to lead to memory thrashing. You don't have enough memory and you're prefetching more than you have. So the more intelligent approach is to actually chunk up the kernel into smaller chunks, whereas each chunk consumes data that actually does fit into memory. And then you can pipeline these prefetches and compute in phases, and then you can basically split it up into these different chunks. And now everything fits. And so you prevent memory thrashing. Again, I'm going to show you the workflow on the compiler side and the runtime side. And in the compiler, again, you bullet the source into LVMIR. Then we have a compiler transformation that extracts the OpenMP loop bounds. Why do we need to extract the OpenMP loop bounds? Because we're going to chunk the iteration space. So we need to know what the iteration space really is. Then we have an LVM transformation to extract memory access expressions. This is required because unless you don't have the memory, because you need to chunk the data prefetches corresponding to the chunked iteration space. Then, as with the previous optimization, there's a path that packs this information up and emits a transformed IR that includes these memory access expressions and the loop bounds, and the runtime is going to consume them, essentially. Now the transformed IR is built into the final executable. Now the executable is going to interact with the runtime. And you see right here there's this target, TG target, run target call, which starts the offloading of the computational kernel, and it interacts with the OpenMP target runtime. And now this API call includes the region information being the loop bounds and the memory access expressions. And then the device plugin, this is what the device plugin essentially does. This is how the algorithm really looks like. You have on top, you have this function that computes the amount of chunks that you want to chunk it. So this depends on what your device memory consumption really is and how much data your kernel is using. Depending on that, it determines how much you need to chunk the kernel. Then it basically loops over the total number of chunks, copies the data that the chunk is going to use, and then executes that particular chunk. And then synchronized task waits for the task to complete before you can actually execute the next chunk. Now coming to the experiments, the experimental section. The goal of the experiments is to firstly understand if these optimizations are useful at all. The second or related goal is to see if these optimizations scale with larger data sets, if the benefits scale. As a baseline, we're going to be comparing against demand paging. So we're just demand paging, no optimizations enabled. And the comparisons are going to be against prefetching and pipeline prefetching, where we're going to be chunking the kernel. The benchmarks we're using is the simple Saxpy kernel that I just showed you, and we have the k-means program, which is taken from the Rodinia suite and adapted with the target clauses. The experimental setup thanks to Oak Ridge National Lab for giving us access to their experimental cluster Summit Dev, which has these Pascal P100 cards with 16 GB global memory each, and they're connected with a host with an NVLink interconnect, which has significantly higher bandwidth than PCI Express. On the software, we're using Clang LVM, and we use this from the Clang YKT branch. For the OpenMP runtime, we have Libomptarget, again available with the Clang YKT branch. So first is also Saxpy. Well, on the x-axis, you see the data sizes, and the data sizes increase from left to right. And this shows the data size in terms of the number of elements on log scale. On the y-axis, you see the time as a percentage of the baseline. The baseline, again, being demand paging. The gray bar here is for demand paging, the baseline, and then there's the prefetching and pipelined prefetching. And as you can clearly see, that for all these cases, these optimizations give significant benefit, reduce the overhead significantly. And interesting for this last column, the last column is the case where your data set size is larger than the available device memory, so you're oversubscribing device memory. In this case, you might observe that prefetching doesn't perform that well actually, because you're prefetching more than the data you have. And the blue bar actually performs, when your pipeline performs significantly better. So there's a benefit to actually chunking up the kernel and pipelining the prefetches and the compute. Now k-means. Now with k-means, I'm going to show two different results to give some insight. So this is the k-means for 10 iterations. Again, on the x-axis, you see different the total number of points on log scale, so points that you're trying to cluster. And on the y-axis, you have time as a percentage of the baseline. And again, you see that across all these columns, prefetching and pipelining performs reasonably well. For the last column, the one that does not fit in device memory, a similar observation that pipelining performs better than prefetching, merely prefetching, particularly because everything fits and then you're not thrashing memory. But this is an interesting result. So we have k-means with 20 iterations, so increasing the number of iterations. For all these columns, you still see prefetching and pipelining giving performance improvements. For the last column, there's your data doesn't fit in device memory. Interestingly, demand paging is actually performing the best. And the particular reason for this is that demand page, when you have these multiple number of iterations, the hardware learns to use a more optimal strategy. And in this particular case, k-means, because you have these multiple iterations, and the data across all these iterations is reused essentially. So if the hardware chooses to use an optimal eviction policy, then the data communication is reduced and demand paging actually performs better. The solution to this is using more sophisticated pipelining strategies in the software, and we're working on this is current work. To summarize the whole talk, so we developed an UVM compatible OpenMP framework that works with GPUs, and we show that performs well. We've implemented these two optimizations particularly to reduce the page fault processing overhead, and two optimizations for prefetching and pipelining. And we see that these optimizations perform pretty reasonable on our benchmarks. At future work, as I said with the previous slide, we're going to be working on more sophisticated pipelining strategies that enable better performance. Sure.
So I need a quick follow-up. How are you determining the memory that's being touched and its association with the kernel computation?
So we're using the data map clauses. So the programmer, so the assumption here is that the programmer is providing you the data map clauses. So if you're using OpenMP for accelerators in a non-UVM setting, you have to use the data map clauses, right? So the argument right here is, even though you could use, with UVM you don't really need those clauses, but having those clauses actually can significantly improve performance because they act as a hint to the runtime, and it could prefetch that data in advance.
So you're just saying, since we have UVM, we don't have to do the actual data motion other than using the prefetch?
Yes, but I mean, in the sense that with UVM,
one of the things we're planning to add in 5.0 is the ability to basically say, oh, well, I've got UVM assume that my virtual addresses are consistent and sort of treat them correctly. So then you can use the map clause.
Mm-hmm.
The map clause is providing semantic information as to whether. Oh, the map clause is definitely still useful, but there's a lot of programmers that want to be able to assume that basically it avoids having to do a lot of work for decoding and things like that. You don't have to go chase down the language.
So here he's using the map clause to move pages. So
Yeah.
Instead of traditionally we use the map clause to
No, he's using the map clause to identify what data is being touched. And then he's moving the pages with the prefetching.
yeah, that's right. But this is a key for moving pages.
Yeah.
And your baseline, you're not doing anything to the page, you're starting the system.
So essentially, we do have, so there's where the compiler pass came into the picture, that we do have a compiler transformation, or we're basically profiling the application or representative endpoint, seeing if the data that is mapped on has a higher likelihood of being accessed. If it doesn't have a high enough likelihood to be accessed, we do not copy it. What probability is high enough to be prefetched is completely hardware dependent. You know, if you move from one interconnect to another interconnect, this constant will basically change.
Yeah.
Yeah. Sure.
Sorry to repeat the same question. Have you considered the impact of multiple GPU products?
That's future work.
Really, you can get bigger space, more memory, right? But it sounds to me that we need, there's enough difference in situations that we're going to need to somehow provide a switch, or whether it's a compiler or an environment providing a switch, allow you to choose which method you're using, unless we have learning, some sort of learning.
By which?
Is there any intuition? I mean, you spoke about what you're learning, what you're understanding, but is there any way to tell programmatically which techniques you use?
And by which technique you mean prefetching versus demand fetching?
Yes, right.
So yeah, for that purpose we profile the application. So based on the data access probabilities, we choose to either prefetch or demand page. If the data is less likely to be accessed, then demand paging is actually more useful, because by prefetching you're copying more data than you're using, and then the data communication time dominates, and so it's not useful. Any more questions?
Maybe I understood it wrong, but your performance numbers showed basically you had 100% were if you used the paging mechanism. So did you also compare it to explicit copying? Because I would guess that the paging is somehow adding overhead, and the question is, do you compensate this with the prefetching? So do you come to the baseline where you explicitly copy, or is it?
So we did do comparisons with the page, with the old approach, right, where you had to actually just copy the data, right? And the performance was very comparable to prefetching, so it didn't really make sense to add it, but the performance is pretty much the same with prefetching. So UVM is worse than that. UVM is worse than doing a CUDA malloc, not allocating in UVM and then copying it. And so that is why UVM does beg the question that we need to have these optimizations to have comparable performance.
Okay, so but with prefetching you come close to what would be best.
Absolutely, yes.
Any further questions? So, thank you.
Thank you.